Hi-oh, here we are again. Last podcast for the unit. Conservation of the big Mo. Momentum. In order to talk about conservation law, we first have to talk about types of collisions. As something suggests, if it's inelastic, it means it doesn't stretch apart. It doesn't come apart. They're stuck together. When something is elastic, it's kind of bouncy, isn't it? Well, this isn't bouncy. They stick. So you start apart, and when they collide, you have a collision. They stick together. Elastic, they bounce. Notice the animations. They could be coming towards each other. They could be moving away from each other. You could have one that's standing still and the other one moving. They start apart, they end apart. And then, of course, an explosion. Everything starts at rest, then they move in opposite direction. There's the ricochet of the gun. The gun kicks. Right? Doesn't kick as far as the bullet kicks forward because of the mass difference. So there's our types of collisions. In every single case, we can talk about the momentum of each object. That momentum is conserved. And I like the word Tunstafel. There's no such thing as a free lunch. In other words, you're not going to get something for nothing. Instead, exactly what you start out with is what you will end up with. Case of the Newton's cradle. We have one ball going in, it hits, and you get one ball going out. What happens if we put two of them in? You should get two out. There's five hanging there. What if we put four in? Yep, you guessed it, four coming out. So, the law of conservation rests heavily on that idea of what you start out with is what you end up with. I have a girl on a skateboard with a basketball holding it. They both have an initial momentum. They're stationary, momentum of 0. So the combined momentums of the system is 0. Afterwards, the combined momentum will still be 0. How is that possible? This one has a big mass. This one has a little mass. You already know what's going to happen. Which one moves the farthest or the fastest? The ball. So big velocity, little velocity. See, they really do. They have the same momentum, but one's to the left, so it's negative. The other's to the right. It's positive. They'll cancel each other and make 0. A gun is no different. System's at rest initially. The gun and the bullet are both 0. But remember, the gun kicks back. It has a, relative to the bullet, a big mass and a little velocity. The bullet has a big velocity and a little mass. One's to the right and the other is to the left. It's still 0 when you add up the momentums of the collision after the collision. So let's try this. Let's do an example problem. A 40-kilogram girl is standing still on a 150-kilogram boat. She steps off onto a dock, and the boat moves backward at 0.3 meters per second. How fast did she step off the boat? My suggestion is to draw a picture, a before and after, labeling things along the way. So we have this boat, and we have a girl on the boat. I'm going to label it. Her mass is 40 kilograms. She's standing still, so the velocity is 0. The boat is 150 kilograms, and of course, it's still as well. That's before. The collision is when she pushes off the boat. So the boat moves backwards, and she moves forward. Did her mass change? No. Did the boat's mass change? No. But the boat moved backwards, so it has a new velocity of 0.3. Backwards should be negative. We want to know what is her velocity. It's just a matter of plugging things in to the formula. Mass, the boat is 150. The velocity of the boat initially is 0. Mass of her is 40. The velocity of her initially is 0. Mass of the boat is 150. The velocity afterwards is a negative 0.3. The mass of her afterwards is 40. The velocity is some unknown. It's just a matter of solving now for x. You'll find that that's 0 and that's 0. This whole left side is 0. Let's try it now. Oh, by the way, this type of collision, what's going on? Is it inelastic, elastic, or explosion? It's an explosion. They start at rest and they end up going at different directions. Okay, if the girl's mass were to increase, what would happen to the recoil? We know that the momentums are equal, right, of the boat and the girl. So as we increase her mass, right, her velocity has to get smaller so it can stay equal. So her mass were to increase. She doesn't go as fast, but the boat certainly does. She becomes the gun, and the boat becomes the bullet, so to speak. What about this situation? A 1,300 kilogram train. So here it is. Mass is 1,300. Moving at a velocity of 2.6 meters per second. Runs into a stationary train with the same mass. Notice I'm writing stuff out, because we know that mass times velocity, the momentum of the first object, plus the momentum of the second object, has to equal the momentum after the collision of the first object plus the momentum of the second object. If they connect, what is their combined speed? So we don't know, but they're moving together. So they're both moving the same speed. So here we go. 1,300 is the mass. Velocity is 2.6. Mass is 1,300. Velocity is 0. Mass is 1,300. The velocity is some unknown. Plus the mass is 1,300. Plus the velocity is unknown. If we look at the right side, 1,300x plus 1,300x is 2,600x. We know this is 0 over here. 1,300 times 2.6, whatever that equals, and eventually you'll solve for x. What type of collision? They stick together, so it's an inelastic. A 5 kilogram bowling ball traveling to the right at 2 meters per second. So here it is. Mass is 5. It's traveling at 2 meters per second. Collides with a stationary 1.4 kilogram bowling pin. Velocity is 0. It's stationary. This is before the collision. If after the collision the pin moves off to the right, so here's the pin, it's going to go off to the right, the mass hasn't changed, but the velocity is 3 meters per second. The ball, which has a mass of 5, what is its velocity? Well, again, mass times velocity of the first object plus the mass times the velocity of the second object, so the complete system here has to equal the complete system after. So 5, 2, 1.4, 0, 5, what we're solving for, 1.4, and 3. Solve that out, and you'll get your answer. So let's look at things quantitatively. We have a train. This one's stationary up here. This one has momentum. Think what's going to happen when they connect. The mass becomes twice as much. So 2 times the mass. So what's going to happen to the velocity? If you suddenly double the mass of it, the velocity should be less. In fact, should be half. Momentum is mass times velocity. Remember, the momentum of the system isn't going to change. This stays. Suddenly, if you make this twice as much, this one has to be half as much. The teeter-totter, right? Got to keep it balanced. Can't change momentum. The momentum of the system doesn't change. So a moving car runs into an identical car at rest. They couple together. How much does it change? Again, we have twice the mass, therefore half the velocity. And what about this situation? We'll show you the clip in a moment. 2 identical trains moving at the same speed. They smash into each other in a head-on collision. So one train moving this way, it's identical to this train moving the other way. What's going to happen? They stick together. Tell me about the velocity. This has a positive momentum, right? This has a negative momentum. And they're identical in mass and identical in speed. What do you think? All right, watch this clip.